In this lecture, we're going to discuss modular arithmetic, which is based on actually a very important equivalence relation on the integers. So, in particular, for integers, say x and y, we say, so this is the equivalence relation, we say that x is congruent to y. Use this triple equal sign, and in parentheses you say mod m if x minus y is a multiple of m. So x minus y equals let's say km for some integer k. Okay. So two integers are equivalent if they differ by a multiple of m, if they're sort of a multiple of m apart from each other. And again, the way you read this is you say x is congruent to y modulo m, or mod m. Okay. And as I mentioned, this is an equivalence relation. So this is, not only is it a relation, it's an equivalence relation. What does that mean? It's symmetric, it's transitive, and it's reflexive. So it's an equivalence relation on the integers. Let's prove that really quick. So why is it, so it's reflexive. Why is it reflexive? It's because x is congruent to itself. Well, that's what we have to show. Why is x congruent to itself? It's because x minus x is 0, which is a multiple of m. Right? Let's check to see if it's symmetric. Well, if x is congruent to y, that means x minus y is a multiple of m. So if x minus y is km, well, that just implies if you reverse it, y minus x, that's going to be minus km. That's still a multiple of m, of course. So it's symmetric and it's transitive. This one's a little bit trickier. So transitive, remember we're assuming x is congruent to y mod m. And y is congruent to z mod m. So y minus z equals lm, let's say, not necessarily the same k. Well, that implies we want to show that x minus z is a multiple of m, and we can do that by adding these two equations. Right? These are just equations in the integers, so we can add them together, and we get x minus c is specifically what multiple of m? It's k plus l times m. So indeed, it's multiple of m. So that's an equivalence relation. And why do we care about equivalence relations so much? We care because it allows us to partition the integers into equivalence classes. So yeah, the whole point of this is, so the equivalence relation, it partitions all the integers into equivalence classes. And let's take a look at those equivalence classes. Remember, an equivalence class is just a set of, in this case, all the integers that are congruent to a given one. So for example, let's just fix m to be a number to make this easier. So let's say m is a number 3. Well, then we have an equivalence class. Let's look at one containing 0. Well, what numbers are congruent to 0 modulo 3? What numbers differ by 0 by a multiple of 3? Well, just the multiples of 3 themselves, right? So 0, 3, 6. I'm just writing out various numbers that are in this equivalence class. We have negatives too. And we can denote this, the equivalence class, brackets. This is a notation that they use for equivalence classes. Sometimes we also write 0 bar, so we can do either one. So this is this set, just all the multiples of 3. And then we can look at the equivalence class of 1. 1 is not in here, right? So what is in the equivalence class of 1? Just all the things that differ from 1 by a multiple of 3. So essentially you start at 1, you count by 3s in either direction. Minus 2, minus 5. Okay. And then the equivalence class of 2. Is 2 we haven't covered yet. So 2, 5, 8. I thought I saw 5 there, but it was a negative 5. And then you're going to negative 1, etc. And yeah, so every integer, so this is the point of the equivalence relation. Every integer is in a well-defined class here. And a well-defined class. This can partition the integers into these equivalence classes. And this is it. Yeah, we've covered everything, because if we get to 3, then we're back in the first equivalence class. So notice, yeah, the equivalence class of 3 is just the same as the equivalence class for 0. So it's literally the same set. So these are the same. And yeah, so this number system, what is the number system? So you have 3 numbers basically, 0, 1, and 2. And sometimes you just leave out the brackets entirely. But I just want to remind you that each of these numbers stands for an entire equivalence class of integers. This is called the integers modulo 3. Very important and useful number system. And it's based on, again, this equivalence relation. So I want to point out, though, so people often think about this in a slightly different way than this. So note, especially in computer science, so note we often think about this number system this number system as the remainder. So remainder you get when a number, let's say x, is divided by 3. Okay. In fact, yeah, in computer programming, if you have a number, say 10, and you compute 10 mod 3, it'll give you the remainder when 10 is divided by 3. So it'll give you 1. So essentially, it'll give you there's sort of 3 most important representatives of their respective equivalence classes, 0, 1, and 2. You can think about those as the remainders. But just to emphasize again, there's really nothing special about these 3. Like I could have just as easily said, 6 and then negative 2, 5, for example. So really, these are standing in for an entire infinite set of integers. Okay. Why is this so useful? Well, as I mentioned, it comes up a lot in computer programming. But here's the really useful part. So the really useful part, the really useful thing about this equivalence relation is what? Actually, we can define arithmetic. It's modular arithmetic. So we can define arithmetic on the equivalence classes. You can't always do this in an equivalence relation. This is a really special one. So in other words, I can just take these entire infinite sets and I can add them or I can multiply them. So yeah, we can add or multiply. Also subtract. You can sometimes divide. That's a bit of a longer story, but we can add or multiply equivalence classes. So, for example, we can do things like the equivalence class of 1 plus, we'll have to define what we mean by that, equivalence class of 2, well, that should give us 3. But no, 3 is the same as 0, so you could say things like 1 plus 2 is 0 mod 3. So you often have say things like this. Or 2 plus, you don't have to use one of these, right? You can put any number you want. So 2 plus 5, what's that mod 3? It's 7. So the idea is you just add normally as if they're integers. And then at any time you can replace a number. You can even do it back here. You can replace a number with anything in its equivalence class. So 7 is what? Well, I mean, yeah, 1 is sort of the representative that we have listed there. There's a potential problem with this, though. So yeah, there's a potential problem. I'll say potential because it ends up not being a problem, but we need to prove it. But yeah, what's the issue? Is the arithmetic, is this modular arithmetic well defined? What do I mean by well defined? I mean, what if we chose like there's nothing special about the 2. What if instead of the 2 we chose a different representative, like the 8? And then what if we add to that? And what if instead of the 5 we chose a 2? Well, then we get something totally different. If we add the 8 plus 2, we get 10. So are we always guaranteed to get the same? Notice it did work out, right? 10 is also congruent to 7 modulo 3. But yeah, is it always going to work out this way? Because if it doesn't, then you cannot define arithmetic on the equivalence classes. So yes, the answer is yes, it does work out, but it requires a proof. So let's do that proof. So requires a proof. Careful proof. We need to really make sure it's well defined. Okay. So what do we want to prove? We want to show it doesn't matter which representatives of the equivalence class you choose, you'll always get the same answer. I mean, you won't literally get the same integer necessarily when you add the two representatives, but you'll always get a well-defined equivalence class. You always land in the same equivalence class. You start with the same two. So in other words, like if I think about this as A1 and A2, and this is B1 and B2. I want to show that A1 plus B1 is congruent to A2 plus B2. So assuming, so yeah, if A1 is congruent to A2 mod M, this is what we want to show, and B1 is congruent to B2 mod M, then so I want to prove this implication. A1 plus B1 is congruent to A2 plus B2. Did I do that right? Yeah. Mod M. Okay. Does that make sense? So, I'm going to show this as well defined. It doesn't matter which representative of each class we choose. Okay, let's go ahead and prove this. So proof. Well, let's let A1, A2, B1, B2 be integers, so that so with A1 and A2 belong to the same class. So A1 is congruent to A2, and B1 is congruent to B2 modulo M. Okay, so that's our setup. And then, well, let's just write out the definition, right? That's usually how you start a proof if you're not sure what to do. Just try writing out the definition. So what does this mean? A1 is congruent to A2 mod M. It means A1 minus A2 is a multiple of M, right? This equals Km for some K and Z, and also means that B1 minus B2 is Lm. And what do we want to show? We want to show that A1 plus B1 is congruent to A2 plus B2. In other words, A1 plus B1 minus A2 minus B2 is a multiple of M. But I'm noticing that I think we can set that up by, again, it's the same idea as before, maybe, adding these two equations. So taking the sum of these two equations, we have A1 plus B2 minus A2 minus B2. I remember the proof for multiplication is a little bit trickier, so maybe we'll do that one too. what do we get? We get km plus lm, which is just k plus l times m. So that proves it, right? So, well, let's make our conclusion. So that shows, what does that show? That shows that a1 plus b1 is congruent to, see that its difference with a2 plus b2 is a multiple of m. So they're congruent mod m. Great, yeah, we can end the proof there. So that proves the addition is well defined. But yeah, this also works for multiplication. So it's really a valuable number system. You can do addition and multiplication. This also works for multiplication. But what do I mean works for multiplication? I.e., so like we have the same setup here. It always turns out that a1 b1, the product, is going to be in the same class as a2 b2. Okay. Let's try to prove that. So I don't know. Can I just can I box this part of the proof and just want to avoid writing this all out again? So see this part here, I'm just going to copy verbatim. So right, I'm going to take A1 is congruent to A2, B1 is congruent to B2. That means this, right? So let's go ahead and start there. So that'll be our starting point. Sorry, I just had to recall how to do this. So we want, so we have these two things. We want, actually, this would be a great opportunity to try to pause the video, try to figure out how you can show this. You want to show that this minus that is a multiple of m, just given these two. This is a fun one, I remember. And you can unpause, and I'll try to do it myself. Okay, so I think the idea is we want to get an a1 b1 to appear, right? So I think I want to multiply the first equation by a b1. So I want to multiply the first equation by a b1 and the second by a b2. I'm not sure I'm going to get all the correct terms that cancel out, but I'm just going to do that and hope that it works out. So if we do that, we get what, a1 b1 minus a2 b1 equals b1 km, right? We have to multiply the right side also. And see, then the second one, I think I want to multiply by, wait, I wrote b2. That's not what I want to do. Sorry about that. So I want an a2 b2 to appear, so I think I meant a2. So let's take this one and multiply by a2, so a2 b1 minus a2 b2 equals a2 lm. I'll do the same trick. I'll add them. So we multiply them both by a well-chosen element, and then we add them. So then add. And what do we get? Let's hope this works out. So a1 b1 minus a2 b1 plus a2 b1. Perfect. Those are going to cancel. We get minus a2 b2 is going to equal some multiple of m. A more complicated one this time, but what is it going to be? It's going to be b1k plus a2l parentheses m. Let's see, these are going to cancel. So we get a1 b1 minus a2 b2 is some multiple of m. Therefore, a1 b1 is congruent to a2 b2. So that shows also the multiplication is well defined. So we can multiply them at any time when we're doing arithmetic like this. We can replace any of the numbers here by a representative of this equivalence class, by a different representative, and we'll always get the same answer, at least up to the equivalence class. Okay, so I'd like to show well, just signify we finished that proof 2. We did 2 and 1. I wanted to show you a sort of fun application of this. There are many applications, but it has to do with divisibility rules. Probably many divisibility rules you learned a long time ago, and you might not have any idea why they work. At least that was how it was for me. So divisibility rule for 3 is a famous one. So what is the rule? An integer n is divisible by 3 if and only if so it perfectly detects divisibility by 3. If and only if its digit sum, so sum of the digits of n in standard base 10 notation, is a multiple of 3. Okay. So this I don't know about you, but like this has always seemed a bit strange to me. I wasn't sure why this worked until I learned modular arithmetic. So let's do an example, or let's just do an example of this rule. So if n is a, b, c, like some three-digit number. Actually, I'll do an example. So like 528. Is that a multiple of 3? Well, here's what you do, right? You check the digit sum. It's 15. 15 is a multiple of 3, so 528 is indeed a multiple of 3. So that's how this works. Let's try to actually prove this. So if I write n this way, I'm just doing it for 3-digit numbers for now, but the idea can be extended to any number. So what is the actual number n? Like a would be 5, b would be 2, c would be 8. Well, it's actually 100a, right? So a has a place value of hundreds, plus 10b plus c. And why am I trying to write it like this? Because I want to be able to pick out the digit sum. So what's the digit sum? It's just a plus b plus c, right? And so now I can relate n, the number n itself, expressed in terms of its digit, to its digit sum, right? So there's n, there's its digit sum. Now in modular arithmetic language, what does it mean for n to be divisible by 3? It means that, well, n is in the congruence class of 3. Or n modulo 3, n is congruent to 0 mod 3, right? Because 0 is in the congruence class mod 3. So n is congruent to 0 mod 3. That's what it means. I'm translating this statement into modular arithmetic, right? N is congruent to 0 mod 3 if and only if its digit sum is a multiple of 3, meaning congruent to 0 mod 3. So if a plus c, b plus c is congruent to 0 mod 3. Okay, well, what is n? So n is 100a plus 10b plus c. And again, you can go further out if you have thousands place, etc. But see, here's the point. I see a 10 times b, right? But if I'm in modulo the integer's modulo 3, I can replace that 10 with anything in its congruence class. For example, 1, right? And you can think about remainders here. So 10 is 1 more than a multiple of 3. So it's going to be congruent to 1 mod 3. So see, this is the same as c plus 1b plus, see, the 100 is just 10 times 10, so it's 1 times 1. So 100 is also 1 more than a multiple of 3, so it's 1a. So this is congruent to that, mod 3. we're essentially using we're using the proof that we did, or we're using the statements at least, right? We can replace any number in a modular arithmetic expression with anything in this equivalence class. So these are the same equivalence class, these two things. But that's the proof. That's the entire proof, right? Because this is n right here. What's n? And so if n is congruent to 0 mod 3, well, this is congruent to 0 mod 3 because n is congruent to this. So that's it. So that's essentially why this works. This divisibility rule. And it turns out you can discover other rules. So for example, there's a rule for 11 that's less well known, which says that, well, actually, I won't tell you what it says. Let's see if we can figure it out. So I'll write n as, let's put it 1,000th place this time, just to do something a little bit different. So, but yes, you can prove these in generality. So let's say n is that number. Let's look at that modulo 11. So I'm going to take this. And I'm going to try to fit. So I'm going to look at this modulo 11. And so I can replace the 100, the 1,000, the 10 with simpler numbers. That's the idea. It's still a valid statement, at least modulo 11. So 10, I might as well replace that with -1, right? Because they differ by a multiple of 11. So -1 maybe seems a little simpler than 10. Oh wait, no, 100 is just that 10 times 10. So it's like -1 times 10. Again, it doesn't matter what representative you choose. So we get a -10, which is congruent to 1. So actually we just get plus b. And then similarly, that's going to be times 10 again, so we get back to -1. So we end up with this. And this actually gives us a pretty nifty divisibility rule for 11 if you stare at this. It's saying, so if this is congruent to 0 mod 11, well, so is this, but this is something that's simpler to calculate, right? Because this just has to do with the sum of the digits. It's a little different than that one, right? It's an alternating sum of the digits. So here's, in fact, what we discovered. And we'll try an example with it just to make sure it works. So an integer n is divisible by 11 if and only if it's how do we say it? It's alternating digit sum. How about that? Alternating digit sum is a multiple of 11. I want to say congruent to 0 mod 11, but this is probably how the divisibility rule will be stated. So yeah, what's an example of this? I just want to show you, this is actually a really useful rule. So let's take like 5, let's do a random one, 5, 7, 4, 8. -5 plus 7, I'm just doing this, -4 plus 8. What is that? I have a -9, I have a plus 15, so I end up with a 6. So what do I conclude? No, this is not a multiple of 11. How about 1309? -1 plus 3 minus 0 plus 9 plus 12 minus 1, that's 11. So yes, that is a multiple of 11. And you can check that indeed is a multiple of 11. This works for other size numbers too, so like a 3-digit number, right? 4, 7, 3. You can just do 4 minus 7 plus 3. That is 7 minus 7 is 0. So yes, that one works, because 0 is a multiple of 11. Okay, and there are many more of these that you can discover. Okay, so that's it for modular arithmetic. Thanks for watching.